In today's lesson, we're going to learn about geometric sequences and series, as well as finite sums for geometric series. Previously, we talked about our arithmetic. Now we're going to focus on geometric. A geometric sequence is one where each term is the product of the preceding term and the common ratio r. So if we look at example 1, when we saw a problem like this earlier in the chapter, we would recognize that to get from one term to the next, in each case, we would say that we are dividing by 4. Well, now we're going to think about this from a different perspective. We are going to think of it in terms of a common ratio. And the way that we get the common ratio is by taking any term and dividing it by its previous term. So for example, I could do negative 6 divided by negative 24, which gives me 1/4. I could do negative 3/2 divided by negative 6, which is the same as negative 3/2 times negative 1/6, and that would give me positive 1/4. Now when you're trying to find your common ratio, once you recognize that the sequence is in fact geometric, you can divide any two terms. So looking at this problem, the easiest two terms to divide would be the first two because they are whole numbers. So here I can say that my first term is equal to negative 24, and my common ratio is 1/4, meaning that I multiply by 1/4 to get from one term to the next. Alright, so when we're trying to determine how to identify what kind of sequence we're working with, there are a couple dead giveaways. Number one, to find our geometric sequence, we are going to look to see if I'm always multiplying or dividing by the same number, and that same number that I'm always multiplying by is my common ratio r. If I'm trying to determine if I'm working with an arithmetic sequence, I'm going to look for always adding or subtracting the same number, and that same number is going to be my common difference, d. If neither one of these work, then it is going to be a neither case, and we're just going to look for patterns to find our explicit formula. Examples of this would be when we see powers, like for example, a sub n equals n squared or n to the third, or when we see problems where we have a fraction and maybe there is one pattern in the numerator and another pattern in the denominator, that would be considered in either case as well. Alright, so for our first set of examples, we are going to find the common ratio in the next three terms in the sequence. Alright, so when I look at example 2, I could see to get from one term to the next, I am multiplying by negative 2. So in these problems, I can say my r value is negative 2, and that would mean that my next three terms are going to be positive 48, negative 96, and positive 192. Alright, pause the video and try the next three on your own. Okay, when we look at these three problems, I circled what I would look at to help us with example 3. The first two terms are fractions, and those are not as easy to look at as the integers we have on the last two terms. Like I said, you can divide any two terms to find your common ratio. 28 divided by 7 gives us 4, and there we go, we have our common ratio. Looking at number 4, in all cases we are dividing by t cubed, and we start seeing that we get fractions. If you had written t to the negative 1, t to the negative 4, and t to the negative 7, those values are technically correct, but we want to see you write your answers as a fraction and not with negative exponents. In example 5, in this case, there's a couple ways you can look at it. One way is you can recognize that the x values go from 2x to negative 5x, which is times by negative 5, and the second term goes from negative 1 to 5, also multiplying by negative 5. That's one way you can get your common ratio. You can also take the second term and divide it by the first term, and if you factor out the negative 5 in that first term, we end up getting negative 5 2x minus 1 over 2x minus 1, which further tells us that our r value is negative 5. And again, I apologize that my handwriting is so poor on this video making app. When we try and generate a formula to find any term in a geometric sequence, what we want to think about is how each term is written in terms of the prior term. So if my first term is just a1, and my second term is my first term times a ratio, and my third term is that answer times another ratio, what we start to notice is that the number of ratios that I am multiplying by is one less than the term that I am on. Therefore, if I continued in this fashion, my nth term would be a1 times r, and multiplying by r n minus 1 times, and when we repeat multiply, we can think of that as an exponent. And this right here is my formula, my explicit formula for any geometric sequence. Alright, in this first example, we are given the common ratio and the 11th term, and we want to find the first 4 terms. So just like we did with our arithmetic sequences, we're going to start with our generic formula. And that formula is that a sub n equals a1 times r to the n minus 1. So for this problem, since we're dealing with a sub 11, we can say a sub 11 equals a sub 1 times r to the 10th power. And if we plug in what we know a sub 11 is 972, and r is equal to square root 3. Alright, so if we go ahead and simplify this, square root 3 to the 10th power is really just 3 to the 5th power. So now I have 972 equals a1, 3 to the 5th power. And if I divide, I can find that my first term is equal to 4. Since I know that my r value is root 3, then my first 4 terms are going to be 4, 4 root 3, 12, and 12 root 3. Alright, now if we look at number 7, here we are given 2 different terms. In our arithmetic sequence notes, when we had 2 different terms, we wrote a system. And we're going to do the same thing here. We can say that a3 equals a1 times r to the 2nd power, and a6 equals a1 times r to the 5th power. Now if we plug in what we know that a3 is 36, so 36 equals a1 r squared, and a sub 6 equals negative 121.5, a1 r to the 5th. Alright, now this one's a little bit harder to solve. We can't use elimination like we did with our arithmetic sequence because we don't have linear equations. So what we're going to do is we are going to isolate the a sub 1 in the first problem and plug it into the second. So we can say that a sub 1 equals 36 divided by r squared. I'm going to take all of that and plug it in right here. So that ends up looking like negative 121.5 equals 36 over r squared times r to the 5th. And then at this point, we can see that the r's are going to reduce. We get negative 121.5 equals 36 r cubed. Dividing by 36 gives us negative 3.375 equals r cubed. And then we finish that off by taking the cube root. Now we always want our answers to be in fraction form. The cube root here is going to give us negative 3 halves. And since we wanted to find r and a1, we have now found both of those. Actually, no, we have not. Back that up. My a1 is going to be 36 divided by negative 3 halves squared. And after I get that, we get a1 equals 16. There we go. When we were trying to find our geometric means, this is a lot like the arithmetic means. Basically, we're going to have the same idea for our setup. So if I want to write a sequence that has 2 geometric means in between the values of 12 and 4/9, that's kind of like saying 12 blank blank 4/9. And just like we saw with arithmetic, if I have 2 blanks, I have to multiply by r 3 times. So 12 times by r times by r times by r, so times r cubed equals 4/9. Then I can go ahead divide by 12, and that gives us r cubed equals 1 over 27, and I can cube root to get 1/3. So now, to fill in my missing terms, 12 times 1/3 is 4, times 1/3 is 4/3, times 1/3 again gives me 4/9. What you'll see here is a proof for the sum of a geometric series. Now this theorem is pretty complicated and it's not on your note sheet, so just take a look and follow along as I walk through it. First, we start by taking a look at the basic geometric series. If you're adding all of the terms, notice that the first term is a1, then after that we take the first term and times it by r, times it by r again, and so on. If we look at the finite geometric series, finite meaning it has an ending point, the sum of the first n terms would go all the way until a sub 1 times r to the n minus 1 power. Now if we take this entire pattern and multiply it by r, then we get this line that we see here. Notice that every single term has been multiplied by r. Now here's the tricky part. In order to solve for s of n, what we do is we can take s of n minus r times s of n. So if we take a look at that, you'll see right up here that this part in red is the s of n. The part in blue is r times s of n, and again, s of n is the sum of n terms. Now when we subtract them, what you're going to see is that almost all of the terms cancel off except for the very first term here and the very last term here. So that brings us to this part of the proof down here that I outlined in black. And if we factor out the s of n, then we can divide this to the other side, and that gives us this formula here. Now, are you going to have to show me the proof? No. However, I wanted to kind of walk you through where it came from so that you could better understand it. Alright, a couple things to point out here. First of all, this n is an exponent on r. It is not 1 minus r quantity of the n. Alright, so don't confuse that because that's a common mistake. Because it is not 1 minus r quantity to the nth power, you cannot simplify it with the 1 minus r that is on the bottom. Alright, our last two slides of examples, we're going to go through some practice problems using this formula. This is definitely one of the harder formulas that we will use this chapter, simply because the numbers get to be pretty big. Okay, in example 9, we are finding the sum of the first 7 terms. Now, a couple things that you want to recognize. First of all, we want to recognize that this is in fact a geometric sequence, or series rather, and we can figure that out by taking any two consecutive terms and dividing them. So if we were to do 70 divided by 14, we can get that our r value is equal to -5. And then once we get our r value, we check to see if that same r value will work for all terms. And in fact it does. To move from one term to the next, we continuously multiply by -5. So I now have that a1 is equal to 14 and r is equal to -5. Now that I have that, I have all that I need to find my sum of the first 7 terms. So sum for 7 terms is going to be a1, which is 14, times 1 minus my r value, which is -5 raised to the 7th power, all divided by 1 minus -5. Now there's a lot of tricky things here that we have to watch out for. The first thing is the parentheses on the top. Like I mentioned before, the n is the exponent on r. So if there is a negative associated with r, like there is in this problem, we have to make sure that we apply that exponent first. And when you type this in your calculator, you need to type it in just like this, with the parentheses as such. The double negative that we see here in the middle does not cancel. And it does not cancel right away because we have to first raise that to the power. Alright, so when we go ahead, we're going to just plug this in the calculator right like this. And you need to make sure that you remember to either put parentheses around the denominator or just type it in as 6. We enter this in the calculator and we will get 182,294. Alright, let's take a look at our next problem. So here, again, we're trying to figure out what is my common ratio. So to get that common ratio, we take any two consecutive terms. In this case, I'm just going to take the first two and take one term and divide it by its previous, giving me a common ratio of root 3. To test that, we check to see if I multiply by root 3, do I get my third term? Yes, I do. Alright, so my common ratio is root 3. My first term is 2, so now I'm ready to set up my formula for the sum of the first 8 terms. So I'm going to do A1, which is 2, times 1 minus my common ratio, root 3, raised to the 8th power, all divided by 1 minus root 3. Alright, now as we simplify this, we do not want any decimals. So we're going to go ahead and say root 3 to the 8th power. Think of that like every 2 root 3's equals a 3. So that's really the same thing as 3 to the 4th power. And 1 minus 81 gives us negative 80. So this right here simplifies to 2 times negative 80 over 1 minus root 3. And so far this looks good because that numerator is just negative 160, but we have to rationalize that denominator. So to rationalize it, we are going to multiply by 1 plus root 3 over 1 plus root 3. And that ends up giving us negative 160 minus 160 root 3 over, my denominator ends up being 1 minus 3, which is negative 2. And then we can finalize by dividing everything by negative 2 to give me 80 plus 80 root 3. Alright, for example 11, we are only asking you to write this in sigma notation. So if you recall the other day, we talked about sigma notation requires several things. A starting point, which will say n equals 1. An ending point, since we have a dot dot dot, we end at infinity, and then we need an equation. So to figure out the equation, we want to look to see how am I going from one term to the next. To get our common ratio, we can take any term, divide it by the term in front of us, and we get 2. We check that ratio works. My first term is 3. Alright, so we learned a little bit ago that any term within a geometric series or sequence is going to be a1 times r to the n minus 1 power. So if I look at this problem and I apply that to this, then I would have 3 times 2 to the n minus 1 power. And that's all there is. Now if you look at number 12 is already written in sigma notation. So the sigma here means that we actually want to solve it. And what we want to do is we want to find the sum of the first 10 terms. So we're going to do the first term, which we need to find. To get a1, we're just going to plug 1 in here for n. So we'll have 4 times 3 to the 0 power, which is just 4. So we're going to have 4 times 1 minus. Now to figure out our r value, the r is the ratio, and the ratio is always going to be the number that's being raised to the power. So in example 12, 3 is my common ratio. Now if you're ever unsure, you can always generate the first couple terms of your series or sequence, and then you can find the r value that way. So we're going to do 1 minus 3 to the 10th power, and then all divided by 1 minus 3. Again, we can expect these numbers to be very large. The terms themselves get large quickly, therefore their sum gets large quickly. And we plug this in the calculator, and we get 118,096. Alright, I recognize that this was a tough lesson, and I'm sorry I was not here today to give it to you. But do your best with the homework, and we will answer questions tomorrow.